Okay, welcome back from your break. This is the 6th video in the presentation on Reynolds transport theorem and the radial hydraulic jump interrogator. We've reached the last presentation objective, which is for me to show you guys how to actually run the experiment to measure those important parameters that came out of the derivation for mass and linear momentum conservation for a control volume built around a radial hydraulic jump. So this is the at-home kit, the radial hydraulic jump interrogator. I show two images here. The first one is of the entire system, and then the second one is this image where I've got this red circle, and it's essentially just a close-up of the red circle. I've got it operating so you can actually see the water coming out of the nozzle, and you can see a hydraulic jump formed here on a substrate target. I have labeled all of the important components so that when you guys get to the hydraulic jump interrogator set up for you, you'll know what all the important pieces are. So let's start here on the left, the blown up view of where the hydraulic jump is actually formed. Here is the nozzle. This is the nozzle where the liquid water comes out of. So you're ultimately going to want to measure the diameter of that nozzle, because that is one of the parameters in our equation. This is a target. It needs to be a smooth piece of either plastic or metal with no lip on the end. That allows the hydraulic jump to form in whatever shape it wants to form without a buildup of fluid causing the hydraulic jump to be taller than it normally would. Over here is a drain, so the fluid accumulates in this reservoir and then it drains out and goes to a pump, which we'll talk about in a little bit. And then this thing is quite important. This is the flow rate control valve, which controls the rate at which the fluid comes out of this nozzle. Now recall that we've talked several times about how the volume flow rate, changing the volume flow rate changes the radius or the diameter of the hydraulic jump. So using this handle is how you actually control that volume flow rate and influence the size of the jump. It's important to make the jump big enough that you can actually measure it, but not so big that it spills over the end and essentially all you have is supercritical fluid from the point of contact here all the way over the end of the target. So you do have to adjust the volume flow rate to get a hydraulic jump that's the right size to be measurable. Over here on the right, if we look at kind of the bigger picture, there is a tall 2,000 milliliter graduated cylinder that is a reservoir of fluid that doesn't have any velocity or any turbulence or anything associated with it, so it can spill out of the graduated cylinder through the nozzle quite cleanly and give you a nice clean hydraulic jump without any kind of velocity artifacts in the fluid. There is a pump, so remember the fluid leaves from the drain. It drains from this reservoir down into a pump. The pump pressurizes the fluid and runs it through this Tygon tube back up into our reservoir. And then to determine the volume flow rate, we have here a rotometer, which is our volume flow meter, which tells us the rate at which the liquid water is circulating through the system. So those are all the key components for this experimental apparatus. Now I'm going to run through the steps to take measurements, and then in the final video of this series, video 7, I'm actually going to set up the experiment and run through it so that you can see how all the measurements are taken, so you have a sense of how to do it when you guys come face to face with the experiment yourselves. So there are several measurement steps. Remember, the overall goal, again, we can't lose sight of the goal, is to collect experimental data to validate our mass and momentum conservation expression, which I've boxed here in green. Remember, this expression came from the application of Reynolds transport theorem, mass and linear momentum conservation to a system that includes the radial hydraulic jump. And so what we want to do is measure things like volume flow rate, the radius of the hydraulic jump, the height of the fluid after the hydraulic jump, and the diameter of the nozzle, and then see, once we plug those measured numbers into this equation, if the experimental numbers agree with the theoretical model. So that's essentially what we're going for in taking these measurements, to get an experimental and theoretical correspondence in the measured values. So the first thing we want to do is rotate that blue flow controller on the nozzle to establish an adequate hydraulic jump diameter to measure. So we want to get enough volume flow out of that nozzle that the hydraulic jump has some meaningful and measurable diameter. If the jump is too small, we need to increase the volume flow rate. If the jump is so large that it actually pushes over the edge of the target to the point where there's no subcritical flow on the surface of the target, then we need to reduce the water flow rate so that the jump exists and it occurs on the target. Second thing we want to do then is note the graduated cylinder reservoir water level. We want to make a situation where the fluid is essentially a steady state flowing around the loop of the experiment. So the way that we do that is just look at the water level in the graduated cylinder and note whether the level is increasing, decreasing, or staying the same. We want it, of course, to stay the same. That means that we are in steady state operation. So if the water level is dropping, we want to increase the pump rate to put more water into the reservoir until we reach steady state. And if the water level is rising, that means that we're pumping fluid into the reservoir faster than it's being poured out onto the hydraulic jump target, and so we need to reduce the pump rate in that case. We're going to adjust the pump rate until the water reservoir level remains constant, and then we know that we're in a steady state situation and we can start taking measurements. So the first measurement we want to take then is the volume flow rate of liquid water, which runs through the rotometer, which is on the pumping stand, and we're going to read a value off the rotometer. We're going to record the value of the volume flow rate and the uncertainty in the value, just in case we need to do statistical analysis and uncertainty propagation on the data that we collect. So volume flow rate comes off the rotometer. The next step is to measure the hydraulic jump diameter. It's possible to measure the radius, but given that these hydraulic jumps are a little small, it's better to just measure the diameter and divide by 2. So to do that, we're going to use a set of calipers. We're going to extend the caliper jaws so that the tips of the caliper jaws are coincident with the extent of the jump. The measurement does not need to be perfect. It just needs to be very close, and if it's close, the result should be good. Regardless of whether you're off by a millimeter or too big or too small. Be careful when you're using the caliper not to touch or disturb the jump. As soon as you touch the water with the caliper, the size of the jump will change because you've now disturbed the jump. So be careful not to disturb the jump. Just take kind of an eyeball measurement with the caliper and then record the measured jump diameter and the uncertainty in this value. Note that uncertainty should probably be actually pretty large, maybe the largest by percentage of all of the measured values, because the caliper is a bit uncertain in its measurement when we can't actually get the caliper down into the liquid and find the very edge of the hydraulic jump. Okay, the next step is to find the subcritical water height after the jump, that's H2, and we're going to use a dipstick. So we're going to put the dipstick into the fluid, and we're going to orient it so that its long edge is parallel to the flow direction so that it creates as little disturbance as possible in the flow. We don't want to disturb the flow as we're measuring it because that could unduly influence the geometry of the jump. So we're going to dip the dipstick into the water downstream of the hydraulic jump, and we're going to remove the dipstick and use our caliper to measure the extent of wetting. The extent of wetting then is going to tell us the height of the hydraulic jump, the height of the fluid after the hydraulic jump, and we're going to record that value and its uncertainty. And then the last step, since each individual pair of students is going to just record one set of data, and then we're going to use all of the data to do statistical analysis, the final thing you need to do is report your measured values to the instructor. So the measured value for volume flow rate, for the diameter of the radius of the hydraulic jump, and the height of the fluid after the jump then get reported to the instructor. I will measure the diameter of the nozzle with the caliper, so we'll know that in advance. And with these 3 parameters and the nozzle diameter, we have everything we need to validate this equation. Okay, so that brings us to the end of this video. There's one more where I'm actually going to walk through all these steps with the real experimental apparatus. So please take a break and come back for one more video lecture, and that will be the end. So one more lecture, or one more video. So we'll see you in a little bit for that one. Okay.